welcome to Algebra 2 with Mr. Clausen. Today we are going to go over adding and subtracting rational expressions. So some of the basic things that we're going to talk about today is how to use a least common multiple and how to find those. And then we're going to apply that skill to adding and subtracting a rational expression for practice here. So without further ado, we're going to get started here. And one of the main things that I want to talk to you about as far as finding least common multiples, or the LMC as I'll refer to it in this lesson, is that you want to find how two terms are similar or different from each other. And specifically where this is going to be useful is, comparing denominators. And so just to get started, I want to look at these two expressions and determine what the least common multiple would be for these two, just to simplify this skill. So to find a least common multiple, you need to start factoring things out. So for example, if I'm comparing these two, I need to pull a 3 out of this first term. This would give me x squared plus 3x minus 10 as a given example. And then with this other one, again, I want to find common things easily, or that can be easily pulled out. And this would give me 6 times x plus 5. And then just keep whittling it down. So here, if I split this apart, I go -2 and 5. And I can factor this all the way down to 3 times x minus 2 times x plus 5. And the same will go to here. I can split this 6 to 2 and 3, break it down to every prime possible. All right, and as far as trying to figure out what your least common multiple is, in an example like this, is you want to create an expression that contains every prime that is present between these two subsets. So for example, we can add all the terms from the first one that we have if we wish. So we can go 3 times x minus 2 times x plus 5. All right, and then look at the second one and go, is there anything in here that is not already present here? So for example, I see that x plus 5 is there once. So nothing, that doesn't need to be added a second time. The only way you would need to add it a second time is, if for some reason this was squared here, you'd have to add that, but that's not the case, so we don't need to worry about that. There is a 3 already present here, but this 2 is unique. So if there's anything unique left over in the second term that's not in the first term that you already wrote down, that's all you need to do. And this would be the least common multiple. This is a multiple that shares all the common terms between these two specific expressions. So now let's try that again. So we have this expression here. So we have this term here. So let's factor it out completely. X squared plus 3x plus 2. And we can pull a 2 out of this side. X squared minus 4. And again, 1 and 2. So this means that 5 times x plus 1 and x plus 2 is all the terms on this side. This one's 2 times x plus 2 times x minus 2. And so we have these here. And now the least common multiples would consist of, you have to include everything for the first one here. All right, and it doesn't matter which one's the first one, because then you're just going to compare it to the second one and be, is there anything unique left over? And what I see here is that 5 is a prime and 2 is a prime. So I need to add 2 here just so it has all those primes. And there is an x plus 2 here. All right, so we don't need to double up on that, but there is an x minus 2. So we go and add this x minus 2. And now you have the least common multiples between these two given terms. All right, and so that's what it's looking for if it's asking for a least common multiple. So why is this useful? It's useful because now if we go to adding a rational expression and we have a doohickey like this, really the first question that we have to ask ourselves is, what is the least common multiple between x squared minus 4x minus 12 and 4x plus 8? And part of the reason that we do this is there is a chance that every term with all these components are unique, and that this step doesn't necessarily help us out a ton, But if you are dealing with much larger, more complex denominators, or you're adding it across a huge number of different separate expressions, this will save you a lot of time. So keep in mind that the examples that I'm using here are relatively simple to communicate the idea. But what I'm going to do is I'm going to factor this out just like I normally would. So this is going to be, let's see, if I go 2 times negative 6, that'll give me this distribution. So this will give me x plus 2, x minus 6. So that's completely factored. I can pull out a 4, and this will give me x plus 2. And actually, in this case, I see a little bit of time is saved in this given circumstance. So now when I'm doing my least common multiple, keep in mind that these are 2 2's, but that doesn't necessarily matter in this case. So if we go x plus 2 and x minus 6, that's all the terms here. And now I'm going to see if there's anything else that's unique. Well, the 4 is here. So we'll go 2 times 2. X plus 2 is shared. So this is the least common multiple. So how do I apply that now to this given situation? Well, if I know that this has the x plus 2 and the x minus 6, what I'm going to do is I'm going to multiply this expression by a factor of 1 that goes and makes that. So one way that I would typically go through this is I would kind of do the canceling in my head before I even get started here. But if I multiply both of these by 2 times 2 all over that, what I'm going to find is that I'm going to be making the denominator for both of these terms this least common multiple. That's the goal, is you're trying to use this as a pathway so that both of these denominators match this least common multiple. So what do I need to multiply this denominator by to get this least common multiple? Well, these are already present, so now I just need to multiply by 4 over 4. That'll make this into this least common multiple. And so now, if I'm looking at the other side, what do I need to multiply this by in order to get this least common multiple? Well, the 4 and the x plus 2 are already there. So the only thing I need to multiply this least common multiple by is the x minus 6. And so now what I can do is with this multiplication, I know everything's going to have the same denominator now. That's what's the whole target here. So I can go and I can write this out and say, 2 times x plus 2 times x minus 6. That's my least common multiple. Everything's got that denominator now if I perform this operation. And then on this side here, what I'm going to have is I'm going to have the 4 over here in terms of what is going on in this specific case. And what I'm also going to have here is I'm going to go 3x times x. That should give me 3x squared and 3x times negative 6, and that's going to give me negative 18x. And with this given circumstance now, I can go, I should rearrange this in standard form. And so what my final answer should look like is 3x squared minus 18x plus 4. And I think I'm just going to multiply those two 2's together. But I am going to leave the rest of this factored. And this would be my final answer involved with combining these two separate rational expressions and adding them together. So now one last example before I wrap up for today. So with this given situation, I'm taking the same idea of the least common multiple. So I'm going to go 3x squared plus 36x plus 105 and 6x plus 30. So pull out the 3 and I'll get x squared plus 12x. This is supposed to be x. 105 divided by 3 is 35. And pull out the 6. You get the x plus 5. The 6 will give me a 2 and a 3. If I go 7 and 5, those are, if you add those multiples up, that gives you the 12. another factoring technique there. So now we'll go 3 times x plus 7 times x plus 5. And now let's find our LCM, least common multiple. So 3 times x plus 7 times x plus 5. I usually start with the larger one, I guess, if I'm choosing one here. And I'm going to go look over here. I see the 2 is unique, but I already have a 3, so let's go 2 times 3. X plus 5 is already present. So this least common multiple contains all the primes or the binomials present in both of these terms. That's sweet. Super hunky-dory. We're all set. And so now what I'm going to do is I got to multiply 6x plus 30 by x plus 7 so that I can obtain this least common multiple, because, you know, the 6 is already there and the x plus 5 is already there. So if I multiply this by x plus 7 all over x plus 7, that'll get this this denominator equal to the least common multiple. That's what I need to do there. And now this guy, well, shoot, all 3 of these terms are already present. And so now all I need to do to this side, this half, is multiply by 2 over 2. And keep in mind, by doing this, you're able to circumvent a lot of steps. That's why I like this method, is if I multiply each half of the equation by a multiple of 1, because 2 over 2 equals 1, and x plus 7 over x plus 7 equals 1, it allows me to focus my calculations on specific parts of the rational operation that I'm trying to do here, and so that there isn't so much foiling and canceling out and those type of things. So look at those least common multiples, you know, get some practice with that, because once you familiarize yourself with this process is going to be a little bit easier. And so now we just do some basic multiplication. So we go -4 here, minus 3x squared, because 3x times x is x squared, and 3x plus 7 is 21x. And then your least common denominator is all these things multiplied together. So I'm going to combine the 2 and the 3 to make a 6. And then I'm going to go x plus 7 times x plus 5. And now we're almost done. What I'm going to do is I am going to finish the subtraction part here by distribution. And I'm going to rearrange in standard form. So I'll go -3x squared minus 21x minus 4 all over the least common multiple. And with that said, that is your final answer in terms of subtracting these rational expressions. I hope this video gave you a nice breakdown of how to use least common multiples to go and do basic rational expression operations. And with that said, let's do some math.